infinity, if you recall, is the boundary of the disk. It's also R union infinity, which is the boundary of the hyperbolic plane. Okay, so there is a really nice theorem which tells you what symmetries are in terms of the circle of infinity. Let me just state it. So theorem, what is the context? I have the circle here and I have three different points on it, P, Q and R, and I have the same circle, let's say, and I have 3 points on it, which is P prime, Q prime and R prime. Okay, they're in somewhat different positions, completely different positions, but they're distinct in both cases. Theorem says that there is a unique hyperbolic isometry take phi, so phi maps D to D or H to H, such that phi of P Q R is P prime Q prime R prime. Okay, so there is a hyperbolic isometry taking 3 points to any given 3 points, and this is uniquely determined by the image of the 3 points. Let's just contrast with the Euclidean case. If this was a Euclidean disk, you could take P to P prime, but that's it. I mean, the distance between P and Q would be fixed, so that would be one transitive. So in this case we would say it's exactly 3 transitive, the group of isometries on boundary D, which is S1 infinity. But in fact, with the proof we'll go to boundary H instead. This picture was nicer, so I wrote it this way. Let's just make a couple of reductions. So it's enough to show this in the following way. You first fix ABC as you like, and we'll fix some particularly nice ABC, and take P prime, Q prime, R prime to be ABC. That is to say, if I take my favorite 3 points ABC, which in fact we'll take 0, 1 and infinity, I should say the tuple rather than the set, in boundary H, which is S1 infinity, and we'll take PQR is so why is this? Because if you can map PQR to ABC, then you can also map P prime Q prime R prime to ABC, and composing with the inverse you get a map from PQR to P prime Q prime R prime, and the uniqueness again follows by a similar argument. So as I said, we show there exists unique phi mapping A, B, C to 0, 1, infinity, and A, B, C are now going to be points in boundary H. Okay, we first show existence, and then the uniqueness. We'll show uniqueness also for a specific value, as we'll see. Okay, so let's look at existence. Well, what I'll do is we'll write, so phi of course is isometry here. Okay, what we'll do here is we'll write phi as a composition of various maps, and these maps are going to be so I could write just a single map, but it will become clearer. It will become clearer if I write it as a composition. So firstly, if C is not infinity, okay, so you use Z goes to -1 by Z minus C to map it to infinity. Okay, so hence, so you can assume C equals infinity. So we apply one map first, which will send C to infinity. Okay, now let's go a little further. So here we have the real line, and we have C equals infinity, and we have points A and B. Okay, and here we have infinity, and we have 0 and 1. Now in the picture I have drawn a to be before b. Okay, but if a is greater than b, we apply a reflection. So this lets us assume a is less than b. And then finally take z maps. Well, I want to send a to 0, so I subtract a. But then I want to send b to 1, so I'll divide b by a. Okay, I could have in fact incorporated the first step in such a formula, but I think this is a little clearer, so I will do it this way. Okay, so what we have done is we have shown there exists such a map. What about uniqueness? Well, uniqueness is easy. Yes, well, it suffices to show, again by using compositions, show that if phi mapping suppose phi maps, of course, H to H isometry such that it sends the triple 0 1 infinity to 0 1 infinity, then phi actually is equal to the identity. Well, I mean, this is really easy to see. First of all, there is a small subtlety. Phi preserves cyclic order on boundary H, which is boundary D. Okay, why is this? What do I mean by this? I have 3 points which I am going to call 0 1 infinity. Okay, these correspond to 0 1 infinity. Well, going from 0 to 1 to infinity is going counterclockwise, and what you know is that phi is phi mapping S1 infinity to S1 infinity is a homeomorphism. Okay, and if it takes 3 points to themselves, then it takes the counterclockwise direction to the counterclockwise direction. So it has to be either orientation preserving or orientation reversing. Because it's a homeomorphism, it has to be orientation preserving. Okay, so this implies that phi maps Z to AZ plus B by CZ plus D. So I have not written down a formula if it's not a fractional linear transformation but orientation reversing, but we know it's orientation preserving. So we have already deduced that it's a fractional linear transformation. These are all the isometries of hyperbolic space. Yeah, we didn't actually prove this, we proved the other way around, but it's an easy exercise to prove this. And so what we deduce from this is now, so 0 maps to 0, sorry, infinity maps to infinity first, implies, well, there's no denominator, phi maps Z to AZ plus B, and 0 maps to 0 and 1 maps to 1 implies that in fact phi maps Z to Z. Because the image of 0 is B, that should be 0, and the image of 1 is A. Once you know that image of 0 is B, so you're once you know B is 0, so you're done. Okay, so we've seen that the group of isometries has a very nice description in terms of boundary. Given any 3 points and any other 3 points, there's a unique isometry which takes one to the other. Okay, so we look at one more aspect of infinity, which is what we would call ideal triangles, which is extremely important in many contexts in hyperbolic geometry and its applications. Okay, but I want to say one thing about that which follows from what we just observed. So what are ideal triangles? These are triangles with all vertices at infinity. Okay, so let me take 3 points at infinity, P, Q, and R. Okay, and then there are geodesics that join them. Incidentally, one thing we'll see which we'll use later is, remember that both these geodesics are perpendicular to this line. So each of these angles is actually 0. So this is a curious object. It has all its vertices at infinity, even though there are 3 geodesics. There's no Euclidean analog of this. All its angles are 0. Well, the corollary to our theorem is that all ideal triangles are congruent. Now, congruent means isometric. Actually, it means more than that. It means there's an isometry of the whole space, the hyperbolic space, which takes one triangle to the other. In particular, it restricts to an isometry of these. This is an immediate consequence of the 3 transitivity. Okay. In fact, 3 transitivity says that there is a unique isometry which takes one hyperbolic triangle to the other.